Welcome to the final video or Unit 3, Optimization for Training Deep Models. The terrain, non-convex landscapes, local minima, saddle points, vanishing and exploding gradients. The vehicle's parameter initialization y0 is a disaster and the Xavier and he recipes, then adaptive learning rates from other 2 ADAM. They optimize are running the modern world. 2 quizzes and the unit wrap up await. Let's finish strong. Part 2 Optimization for Training Deep Models. Here's the framing. Training a network means searching a landscape with a billion dimensions for the lowest value. This part of the unit maps the terrain's hazards and engineers the vehicles to cross it. The route first, training stated as pure optimization 1 formula. Then the 4 hazards, non-convexity, local minima, saddle points and the vanishing exploding gradient twins. Then parameter initialization y starting at 0 is a disaster and the Xavier and he recipes that fix it. And finally adaptive learning rates Adagrad and Adam, the optimizer running most of the world's training jobs right now. By the end the incantation Adam with he initialization becomes engineering you can defend. Let's map the terrain. Training stated as pure mathematics 1 line. Theta star equals Rg min, or J of theta. Find the parameter values that minimize the loss. That's the entirety of training. The cost, theta, all the learnable values, weights and biases. J of theta, the loss function measuring how wrong the predictions are, smaller is better. Theta star, the optimal setting, the treasure we're hunting. To field the scaled GPT class models have theta with roughly 8 trillion entries. That argmin is a search in a trillion dimensional space. Every trick in this chapter exists because that search is brutally hard. One honest subtlety from the textbook, worth a sentence, what we truly want is low test loss, but we can only minimize training loss. Bridging that gap is what part 1 regularization was for. The 2 halves of this unit are one machine. Why does the landscape fight back? 4 hazards, learn them as a map legend. Hazard A non convexity. A convex problem is one clean ball, one minimum, guaranteed findable. Neural network losses are not convex, they're mountain ranges, many valleys, many peaks, no guarantee of finding the global best. Hazard B local minima, a dip that's lowest nearby but not lowest overall. The slope hits 0, gradient descent declares victory, while a better valley waits beyond the ridge. Hazard C saddle points, slope 0 but not the minimum, a horse saddle, downhill ahead, uphill sideways, and the shocking fact of high dimensional geometry. With a million parameters, saddles vastly outnumber local minima. To be a true minimum, you must curve upward in every 1 or million directions at once. Hazard D the twins, vanishing and exploding gradients, signals that shrink to nothing or blow up to infinity as they travel through depth. The rest of this part is medicine for these 4. Initialization fights hazard D at birth next. Before training begins, every weight needs a starting value. And that choice matters far more than it looks. Attempt 1 initialize everything to 0. Sounds neutral, clean, and it's a complete disaster. Here's the chain, follow it carefully. Identical weights produce identical outputs, which produce identical gradients, which produce identical updates, so the weights remain identical forever. Every neuron in the layer learns the same thing. Your 100 neuron layer is secretly 1 neuron. This is the symmetry problem, no effective learning ever. My analogy, hiring 100 identical clones, same thoughts, same mistakes, same lessons. You have 1 employee, salaried 100 times. Attempt 2 random initialization. Symmetry broken, different neurons, different features. But now a new problem, values too large, and signals explode through the layers, too small and they vanish. Randomness needs its variance chosen intelligently, which is precisely the recipe on the next slide. The 2 initialization recipes that solved it, Xavier and he. Xavier initialization, Glorat and Bengio, 2010. The idea, keep the variance of the signal roughly constant as it flows through layers, neither growing nor shrinking. The formula, variance of W equals 1 over fan in plus fan out, the neuron counts entering and leaving the layer. Best partner sigmoid and TNH activations, which are sensitive to large inputs. HE initialization, he et al., 2015, designed for ReLU networks. Variance equals 2 over fan in. Why the 2? Delicious reasoning. ReLU zeros all negative inputs, killing half the signal's variance. He initialization simply doubles the input variance to compensate. Poetry in arithmetic. The pairing rule to memorize sigmoid or tan, Xavier, ReLU. Here, and a comforting secret, modern frameworks default to these. You've been using he initialization all along, now you know why it's there. On to the optimizers, starting with the question that motivates them all: why should the learning rate adapt? Basic gradient descent uses one fixed rate e2 for every parameter forever. Two problems with that. Problem 1: the Goldilocks dilemma from Unit 1: too large, unstable, too small, glacial. Choosing one good number is already hard. Problem 2: deeper, different parameters need different rates. In language models, the embedding for the updates millions of times, it needs tiny careful steps. The embedding for serendipity updates rarely, each update must count big steps. One shared rate shortchanges someone? The analogy: one fixed stride length for climbing stairs, walking on ice, and crossing a river. Absurd. You adapt your step to the terrain. Adaptive optimizers do exactly that per parameter, automatically, thousands or times a second. The lineage will follow Adagrad, then its refinement into Adam. Let's go. Adagrad adaptive gradient descent, the first of the adaptive family. The core rule: each parameter gets its OWN learning rate, adjusted during training. Parameters that change a lot get a smaller rate, braked. Parameters that change little get a larger rate, boosted. The mechanism in one line: each parameter accumulates its squared gradients over time, and its step is divided by the square root of that sum. Busy parameters accumulate a big sum, breaks. Quiet ones full speed ahead. The benefits: exam ready, easy to use, no manual rate tuning, avoids overshooting, robust to noisy data, and outstanding for sparse data. Natural language recommender systems where rare features finally learn at a fair pace. But there's a flaw, and it's fatal in long training runs that accumulated sum only ever GROWS, so every step shrinks toward zero, learning grinds to a halt. The fix: replace the ever-growing sum with a decaying average that forgets the distant past. Add momentum on top and you get the king. Next slide. Adam adaptive moment estimation, the default optimizer of the modern deep learning world. Adam extends SGD by computing individual learning rates for every weight from two running statistics. The FIRST moment, MHAT, a moving average or past gradients, that's momentum, a memory of direction. The second moment, VHAT, a moving average of squared gradients, the per parameter scale, Adagrad idea with a decaying memory. The update on screen: theta minus eta times MHAT divided by root VHAT plus epsilon. Read it as the numerator says where to go, the average direction, the denominator says HOWFAR, per parameter. Momentum plus adaptivity in one line. Officially, Adam combines Adagrad and RMS prop. The picture: a ball rolling downhill with memory. Momentum carries it through small bumps and noise, while per direction breaks tame the steep slopes. And the practical magic that made Adam ubiquitous: the default settings: learning rate 0.001, betas 0.9, and 0.999 work almost everywhere. That's why every tutorial simply types optimizer equals Adam. Quiz for an initialization murder mystery. A deep ReLU network trains painfully slowly, and inspection reveals every neuron in each layer computing identical values. What went wrong at initialization and what's the right fix? A. Weights too large, switch to Xavier. B. Weights initialized to 0, the symmetry problem, use he initialization instead. C. Learning rate too small, switch to Adam. D. Too much dropout, reduce the rate. The clue is the word identical. What single cause makes every neuron a clone? Pause and solve it. The answer is B. Zero initialization, the symmetry problem. Fix it with he initialization. Identical values across a layer is the fingerprint of symmetry. Identical weights give identical outputs, identical gradients, identical updates, identical forever. The layer collapses to one effective neuron. And since this is a ReLU network, the right random recipe is he variance to over fan-in, compensating for ReLU killing half the signal. The others don't produce clones. Overly large weights option A cause explosions, not symmetry. A small learning rate option C trains slowly but neurons still differ. Dropout option D adds randomness, the very opposite or identical. Worth asking, would Xavier also break the symmetry? Yes, any random init does. He is preferred here specifically for the ReLU variance factor. Diagnosis and prescription both matter. The final quiz, a whole unit synthesis. Match the tool to the job. Which pairing is correct? A. Bagging reduces bias, boosting reduces variance. B. L1 gives smooth small weights, L2 gives sparse exact zeros. C. Bagging reduces variance, boosting reduces bias. L1 gives sparsity and dropout is an implicit ensemble. D. Early stopping needs the test set, dropout stays active at inference. One option gets every mapping right, the others each swap a famous pair. Take your time, this is the whole unit in one question. The answer is C, the only option with every mapping correct. Walk it through. Bagging trains independent models on bootstrap samples and averages random errors, cancel variance drops. Boosting trains sequentially on previous mistakes, systematic errors get corrected, BIS drops. L1's absolute penalty drives weights to exact zeros, sparsity. And dropout trains 2 to the n weight sharing subnetworks an implicit ensemble. Option A swaps bagging and boosting. Option B swaps L1 and L2. Option D commits two sins at once. Early stopping uses the validation set, never the test set, and dropout switches off at inference. If you got this one right, you haven't just memorized the unit, you've organized it. That mental taxonomy is exactly what the exam, in real practice, will draw on. The 10 takeaways or Unit 3. See how many you can complete before I do. Regularization, anything that cuts test error without cutting training error. L1 versus L2, sparse exact zeros versus small smooth weights. Penalty equals constraint with alpha as the automatic thermostat. Augment and perturb, teach invariances through data augmentation, noise in 4 places. Share parameters MTL trunk and branches, tying in CN and NIS and RNNS. Dropout random amnesia in training, full squad with scaled weights at test. Ensembles, bagging cuts variance, boosting cuts bias, stacking blends types. Adversarial and tangent FGSM attacks, invariance penalties. Initialization, never zero, Xavier for sigmoid and Tarn, he for ReLU. And add-in momentum plus per parameter adaptive rates. The modern default, 10 cards. The densest unit of the course, and you now hold the full toolbox. Going deeper, and this unit's reading list is genuinely historic. The textbook, chapters 7 and 8 at deeplearningbook.org, free, forever. The papers, each one changed the field, each surprisingly readable. Srivastav 2014 Dropout. Gorat and Bengio 2010 Xavier Initialization. He 2015. Kingma and Ba 2014 Adam. And Goodfellow 2014, The Adversarial Panda itself. But the assignment I most want you to do, the 4-way experiment. Train the same small network 4 ways, no regularization. L2 only, dropout only, both. Plot the 4 validation curves side by side. 30 minutes of work and you will see the overfitting gap close before your eyes. Regularization stops being theory the day you watch it work. For dessert, distill.pubs why momentum really works, an interactive optimization masterpiece. And that's Unit 3 complete. You now own the anti-overfitting toolbox: penalties, data tricks, architecture tricks, ensembles, dropout, and the optimization machinery, smart starts and adaptive steps that makes deep training actually work. Next unit we point all of this at images, and I'll leave you with the teaser question. 1,000 by 1,000 pixel image, fed to a dense layer, needs a billion weights per neuron, yet the CNN handles it with just 9. How? The answer is parameter tying from this very unit with a telescope. That's Unit 4, Convolutional Networks. Run the 4-way experiment, revisit the 5 quizzes, and I'll see you there. Thank you for learning with me. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.